All right, in chapter 10, we're going to talk about correlation. So one thing we want to think about in terms of correlation is that correlation tells us both the strength and the direction of a relationship. So up until this point, we've been looking at the presence or absence of a relationship between two variables, okay? So we can find out that there's a significant relationship, but we also want to know about how strong it is and which direction it is, okay? So when we think about strength of correlation, we think of it about a scatter plot. So our x variable, independent variable, is on the horizontal line, and our dependent variable goes along the vertical line. Strength increases as the points more closely form an imaginary diagonal line across the center. So correlation can be positive or negative. Okay, positive means both variables move in the same direction. As x goes up, y goes up, or as x goes down, y goes down. Negative means they move in opposite directions. High score on x tends to have a low score on y. What we're also looking at is whether or not it's the plus or minus also represents a straight line. So here we see a scatter plot, right? So imagine you can draw a straight line through those, or as close as it can get to capturing all those points. And here we've got these lines, right? So on the left, years of school, we see a positive correlation. As one goes up, the other goes up. As one goes down, the other goes down. In B, we see that there's a negative correlation. So as years of school increase, prejudice decreases. We also might have what's called a curvilinear correlation. So that's a relationship between x and y that starts out as positive and becomes negative, or starts out negative and becomes positive. So fear of crime tends to be curvilinear. Fear of crime tends to decrease with age until we reach a certain point after our 30s, and then it increases again. So it looks like this. All right, so what do we want to know about correlation coefficients? Correlation runs between -1 and +1, okay? We know that the direction is indicated by the sign, whether it's negative or positive. In strength, the closer it is to 0, the less correlation there is, the weaker the relationship is. And the closer it is to 1, the stronger that relationship is. And 1 would indicate a perfect relationship. So here we've kind of got this nice little chart that can be really helpful. Okay, so how do we test this? We test this with what's called Pearsons R. That's represented by a lowercase r. So we can determine that strength and direction, but we need to have interval level variables in order to do that. We can use a deviation formula and a computational formula, which we see here, okay? These look really complicated, but we've seen most of these before. We've seen x and x bar, y and y bar, right? And we've seen some of these other variables as well. So imagine we want to look at the relationship between the length of a murder trial in days and the length of time in hours that the jury deliberates. And here we have some trials and their length in days and how long the jury deliberated. So here they are plotted out, okay? It seems to indicate a positive relationship with a few exceptions. So Pearsons R is going to tell us how much the jury deliberation is extended with lengthier trials, okay? So it's focused on the product of the x and y deviations from their means. With Pearsons R, we're going to add those products to see if positive products or negative products are more abundant and sizable. So calculating Pearsons R requires us to compute the sum of the product for all the cases. So we have x and y, right? And then we're going to take x minus x bar, y minus y bar, and then we're going to multiply those together. Okay, then our next step is going to be we have to divide it by we have to divide SP, the number we just got here, 39, the sum of the products, by the square root of the product of the sum of squares of both variables. Okay, so now we've got x minus x bar squared, y minus y bar squared. We're going to plug them all right back in, okay? So we saw this on our scatter plot, but there is a positive relationship. As one goes up, the other goes up. And the Pearsons R is 0.667. So it's a fairly strong correlation between these, between how long a trial lasts and how long the jury deliberates. Okay. Now the other thing we need to know is just because there's a Pearsons R doesn't mean it's significant. Okay. So we want to look at whether or not a correlation exists in the population. So it looks like a lowercase case p, but it's pronounced rho. Okay? If there's no correlation, rho equals 0. So to test the significance of an R, a t ratio with degrees of freedom n minus 2 needs to be calculated. And we've got our method right here. Okay? A simplified method would be to compare the calculated R to a critical value found in table H. So let's look. Here we've got a criminologist looking at research on the relationship between juvenile delinquency and subsequent criminality during adulthood. So she chooses 12 offenders with juvenile arrest records, and then she gathers information about their adult arrest record. She's interested in the correlation between the age of first juvenile arrest and the number of arrests between the ages of 18 and 30. Okay, so on our X variable is the age of first arrest, and Y is the number of times they were arrested as an adult between 18 and 30. Okay, so her null hypothesis is rho equals 0, and her research hypothesis is rho does not equal 0. Okay? Okay, so now we're going to set up our data, right? And we're going to find all those numbers that we need. Again, take a moment to look at these slides and walk through and make sure you understand how to calculate this. So we're going to plug it in, and we get negative 0.652. So negative means there's a negative relationship. As one increases, the other decreases, or as one decreases, the other increases, and it's a rather strong relationship, 0.652. Okay, now we've got our degrees of freedom. Now we're going to put that R into this formula to calculate a T ratio. Okay, the T ratio is negative 2.719. Okay, so that's in the table, it's 2.226. So we can reject the null hypothesis here. So yes, it is significant. The younger someone is arrested, the more adult arrests they have, and it's a fairly strong relationship. So in order to use Pearsons R, we need to have a straight line relationship, interval level data, a random sample, and a normal distribution. Okay, now let's think about scatterplots. For a data set that has several variables, a computer can obtain a correlation matrix. Okay, and that's going to give us the interrelationships between several variables. Okay, so below the entry in the second row, fourth column, tells us the correlation of the offender and the spouse's education. The matrix is triangular with the portion above the diagonal is identical to the portion below the diagonal. Okay, so if you look at it here, right, look at the bottom row. The negative 0.30 is the same as the fourth column in the first row. Okay, one pitfall, correlations can gloss over some major violations of assumptions of Pearsons R, so it doesn't tell us if there's a linear relationship. So we do have to look at the scatter plot to make sure there is a linear relationship there. Okay, we're also going to talk about partial correlation coefficients. It's also important to look at whether a correlation holds up when controlling for additional variables. So again, we focus on scatter plots. A scatter plot displays all the information in the correlation coefficient. We can construct separate scatter plots for different subgroups of a sample to see if the correlation observed for the full sample holds when controlling for the subgroup or control variable. So imagine we see this relationship between height and salary, right? And it looks like, wow, the taller you are, the more money you make. But is it possible that there's a third variable that could explain that relationship? Maybe sex explains that relationship. And if we look at the bottom two, we can see that we could see men and we could see women. So if any correlation remains in either of the two gender-specific subplots, the relationship between height and salary is not as strong as we thought it was. So the partial correlation coefficient is the correlation between two variables after removing the common effects of a third variable. And this also ranges from -1 to 1. Okay, and here's our nice little formula, and here's our t-test. So a consultant for a police department finds a -0.44 correlation between performance on a physical fitness test and salary. So this might suggest to us that the department pays a lower salary to those in top shape. But maybe a third variable is playing a role, the number of years on the police force. Right? So when we look at the number of years of police force, it does impact both X and Y, physical fitness and salary. So on the basis of these correlations, the partial correlation of physical fitness score and salary holding constant years on the force can be calculated as follows. We end up with plus 0.17. This T ratio does not exceed the value found in Table C. So we can conclude that the partial correlation is not statistically significant. This is very useful for looking at what we call spurious relationships, okay? So we see relationships between two variables, but they're both actually caused by a third variable. So for instance, there's a correlation between the rate of rape in 1982 and the circulation of Playboy in 1979 for 49 US states, okay? And the R is plus 0.40. Because of this correlation, many observers have asked, does Playboy have an effect on sex crimes? So, as it turns out, they're both related to the rate of homes without an adult female. So after we control for that, we see that our original correlation disappears. And that wraps up the chapter on correlation.